Hi everyone, my name is Pujit. So this session is gonna be about the introduction of Spark. So this is gonna be a series of sessions wherein we discuss about the fundamentals of Spark and try to understand various technical concepts in both theory and in practical about Spark, and how do we write some sample code pieces for a given scenario using PySpark as well as in Spark SQL. So we will try to make use of free resources like Google Colab notebooks to write our Spark application code to practice. And then slowly, once we are done with the basics and once we feel confident about the Spark basics, we will enter into Databricks space where we will start writing our practiced code using Databricks, where Databricks is a company established by the original developers of Spark. So let's get started. And if you feel that the pace of this course is too fast, I would suggest you to refer to the textbook called Spark the Definitive Guide, which is written by one of the co-founders or co-developers of Apache Spark. So, and whatever the content that I'm presenting here right now is referred from that particular textbook and various other web resources. So I would seriously suggest you to refer to those refer to that particular textbook for better understanding. So let's get started. Firstly, let's try to understand what is Apache Spark and how is it a best big data technology ever. Apache Spark is also called as is an unified analytics and computing engine used for parallel data processing of big data in large computer clusters. It utilizes in-memory caching and optimized query execution for fast analytic queries against data of huge sizes. So when you look at Spark and when you compare the Spark with traditional big data technologies like MapReduce or MapReduce based technologies like Apache Hive or Impala or whatever the other technology, there is a huge difference in terms of performance. If you write a Spark application to count number of rows or do a word count problem for a huge amount of data, it might take, let's say, 10 minutes. And if you write the same application using a MapReduce Java code, then it's gonna take a huge amount of time. So as per the official textbook and as per official Databricks documentation, we have an official code saying that when you write the application of Spark, in majority of the times you will see a 10 to 100 times more performance gain in terms of speed with respect to Spark application when you compare it with MapReduce programs. So how is it possible? That's the main question that we need to understand. So Spark utilizes something called as in-memory caching, which means usually when we read the data from a particular file and try to do a certain set of data processing, we usually load the data from the file which is in the secondary storage like the ROM or a hard disk, and then load that into the RAM which is in the main memory. And once the data is in the main memory, then we will use the processor and pass the data from the RAM and do the further processing. Now with Spark, we completely eliminate, or at most times we try to eliminate the data read and write or intermediate reads and writes between each and every phase of execution. Which means, let's say if you want to do a certain data processing, like read the data, remove some set of columns or correct some values or whatever the kind of code that you have written. Now you want to do a set of tasks that can remove or eliminate duplicate records, or they might correct some records or remove corrupt records or fill some null values. Now if you want to do the same in MapReduce, it's gonna take huge amount of time, because once the data is read into the memory, it will do some set of operations which is gonna give you some intermediate result. Now in order to use that result in the next phase of execution, you have to write that data to the hard disk again. Now let's say if you have a file of 10 gigs, and if you try to read the data into the memory for the very first time, it might take, let's say, 1 minute for 10 gigabytes of data. Now you have some intermediate output which is going to give you 5 gigabytes. Now out of 10 gigabytes, you reduce the data to 5 gigabytes, which you have to write it to the secondary storage. And immediately, in order to do the next level of processing in the next phase, you will have to read that 5 gigabytes again. Now, if you continuously do such transformations, which causes a lots of writes and reads from the RAM to the ROM, we are basically wasting a lot of time. Now, what if we eliminate these intermediate writes and get the data once, do all the processing at once, and then write the data at the end? And this can be happened, or this can be made possible using in-memory caching, which means whatever the data that we pull from the ROM will be cached or persisted inside the memory, so that we will apply the series of transformations that we want to apply on the data at once and finally write the data at the end. So this process is called lazy evaluation, which we will talk more deeply in the later parts of the session. But to give you a quick overview and understanding, we can achieve the agenda of fast processing by using in-memory caching, which is the advantage of Spark over any other big data technology. And with the latest versions of Spark, we have more optimized Spark engine, where we have internal optimizers, catalyst optimizer, and various other features available, which provide us more efficient way to process the data. Now, as I was mentioning, in terms of speed, if you write a Spark application, let's say if it takes 1 minute, in majority of the times, the same application written in Spark will be 100 times faster than the MapReduce. And these are other comparisons between MapReduce and Spark. So MapReduce was basically written in Java. Spark was written in Scala. And again, the Scala, the programming language itself, is written in Java programming language. So even though you're using Spark, you're basically running your entire program inside a Java virtual machine. But that doesn't mean you need to learn and understand Java. We can use more user-friendly and interactive and interpreted languages like Python or SQL to easily write our code and test our code to do the data processing, which is one of the best features of Spark, which provides more support to the Spark in the community in the latest market. Now, when you compare the types of processing powers that Spark provides, it's too huge when compared with traditional MapReduce. With MapReduce, you have traditional batch data processing, which means you receive some amount of data over a period of time. You take that data, process the data. But with Spark, you will learn a simple language, and you can adapt that language with multiple types of data processing, like batch data processing, stream data processing, which is also called real-time data processing. And then you also have features of machine learning available within Spark. But if you want to achieve the same three things in traditional Hadoop technologies, you'll have to employ and learn different technologies like Hive if you want to use SQL-like language, and Apache Kafka if you want to deal with stream data processing. And then Kafka is just a messaging system, or kind of like pub-sub architecture. And again, you'll have to employ some MapReduce or Hive or some other technology to do the further processing again. And there is a lot of learning curve with traditional Hadoop technologies. But with Spark, it's very much easier and simpler. The ease of use exactly states that point. Spark is very compact and easier when compared with Hadoop, in terms of implementation as well as in terms of the learning curve that it takes for us to understand and learn and write the Spark application. And when you come to traditional MapReduce, it is very lengthy. And MapReduce obviously doesn't support the caching, which is the major advantage of Spark, which provides the fast feature. Now, if you guys are from Hadoop background, this image clearly states the intermediate reads and writes that are happening from the processor or the main system to the secondary storage, which is HDFS, Hadoop Distributed File System. Whereas in Spark, once you bring the data from the HDFS or any external storage, you'll do the data processing and then finally write it to the external storage like Cassandra or a data lake or a hard disk or whatever that might be. And one more trade-off between a traditional Hadoop technology and Spark is that if you are using a traditional Hadoop technology, you will have to employ or deploy a separate file system in order to process the data. Let's say you have data coming from an API, and you have live data coming in from that system using Kafka. Now, if you want to process that particular data, you have to store the data inside HDFS, which is again a piece of software which provides a specific set of features with respect to storage. It's end of the day, it's a physical hard disk, but the software of HDFS actually duplicates the data for or replicates the data in order to maintain safety, which means, let's say if a file gets deleted, or if a particular server rack crashes, then you want to have a replication of the file, and you do not want to have a risk of losing the data. So that is usually taken care in HDFS. But you can actually have the same set of features with latest cloud technologies in Azure or AWS or Google Cloud. So you need not worry about using or deploying a traditional Hadoop distributed file system when you're working with Spark, because by default, whatever the cloud storage options that are being provided come with that particular features. Now, as I said, Spark is very easy to learn and implement, and Spark supports 5 different language APIs. Since the Spark itself is written in Scala, it supports Scala and Java. And on top of that, we have higher level easy to use APIs with Python, SQL, and R. And as we know, Python has the major support with machine learning in the current market. It's very much easier for us to use Python to write our programs and integrate our applications with machine learning or whatever. And of course, we obviously know that Python is very much easier to learn when compared with Java. And of course, SQL is more easier to learn when compared with Python. But if you learn Python, it's very much easier to learn and write Spark SQL applications. So Scala and Java provide some set of features, and Python and SQL and R provide some set of features. And during the course of these videos, we will mainly use Python and SQL to write and practice our Spark applications. Now, let's try to understand one of the basic fundamental concept about Spark. So Spark has something called as an RDD, which stands for Resilient Distributed Datasets, which means by definition, a resilient distributed datasets are a fundamental data structure in Apache Spark. They are introduced to provide fault tolerance, data distribution, and parallelism, making them well suited for distributed computing environments. And each and every dataset in Spark RDD is logically partitioned across many servers, so they can be computed on different nodes of the cluster. So let's try to understand each and every word, or try to go a little bit deeper into the meaning of an RDD. So RDD is nothing but the basic data structure of Spark, which means, let's say if you are dealing with a programming language like Java or Python, you have some basic data structures like list, tuple, sets, dictionaries in Python. And if you go to Java, then you have data structures like queues, collections, and then arrays, and various other inbuilt data structures that are available in Java, and similarly in other programming languages as well. So these basic data structures are used by us to do data manipulation, to store the data, to move the data, to do any type of data processing. Right. Now, when you create a variable in a particular programming language, you can make use of that variable to do a lot of manipulations on the data, to apply certain logics on your data. Now, you are using that variable with a particular data type associated with it, or a particular data structure associated with it. Now, if you create a variable a is equals to with a square brackets in Python, it's called a list, which is a data structure, which means it provides a certain set of features. When you create a variable with a list data structure, it provides certain set of features like appending the values to the end of a list, or iterating over the items of a list, or changing items of a list because they are mutable, and various other things. Similarly with other data structures. Similarly, when you want to apply a set of transformations on the data, you have to have some sort of data structure that provides us with a certain set of features. Now you might be getting a question, why can't we have a data structure like a list or tuple or dictionary within Spark? Why do we have a separate data structure in Spark, and why is it called as an RDD? Sure, so this should be something that we need to understand. Now, when we are talking about Spark, we are not talking about data processing happening in a single machine. We are talking about data processing happening across multiple machines at the same time. Now, if you have 1 gig of data, and if you want to read the data and then do certain set of manipulations or transformations, let's say you want to read the data and say the first line of the file is a header information, and you have some set of transformations like remove a particular keyword whenever it appears in that particular file. Or let's say you have an Excel sheet where you have rows and columns, and you have column information and then the actual data. Now let's say you want to read that Excel file and then you want to manipulate the data, saying, hey, whenever a name with Pujit comes in that particular file, replace that with a new name. Or let's say whenever you see a column value greater than 100, then filter those records or only pick those particular values or records from that Excel file. Now these are certain set of manipulations or transformations that you might want to apply on that Excel file. Now in order to make this happen, you need to, if you are doing that in a normal computer with an Excel application with 1 gig of data, that's fine. But let's say if you have 10 gigs or 100 gigs of data, or if the size of the file is increasing continuously, now it's a challenge. It's the case of big data. Now if you want to do the same type of data processing using Spark, the data you obviously will employ multiple machines, which are called as executors or workers. Now you will split your data, which is 10 gigs or 100 gigs of file, into partitions, into pieces or into chunks. Now you will take each and every partition or chunk and provide that chunk of data to one worker or one executor or one machine. And similarly, you will take each and every chunk or partition of data and share it across all these executors or across all these workers. Now you will provide the logic or the code that you have written that need to be executed on this entire data to all these executors. Now when I'm saying executor or worker, it means that it's a machine at the end of the day. It's a computer, but you do not have a screen like a typical computer. It's just a set of CPUs to which we are transferring the data and transferring our code to execute on those machines, so that all those machines will execute our code and then give us the final output as a single file if we specify the required configurations in our code. Now, since Spark involves multiple machines, you also need to have a particular set of software features that can provide us the coordination between execution that's happening across these executors. Maybe you might want to move the data across these machines sometimes. That might be a case. Or you might want to sort the values in Excel. If you want to do the same in Spark, you might want to specify a sort condition. And if that is the case, you have to move the data across these machines, across these computers. So if that has to happen, we need to have a framework in place that's gonna provide us the features of data movement and the information exchange between these computers. Now, all of this happens only if we have a proper framework, and that particular framework is nothing but our Spark. And in order to make that happen, we obviously will have a certain set of different features that differ from a traditional machines. Python, Java, Scala, C, C++, .NET, all these programming languages are designed to run on a single machine. And programming languages like Scala are capable of doing distributed data processing, provided that we create that particular feature. But that particular feature is already available with us in the form of Spark, we need not worry about recreating them. We just make use of the features available in Spark, which are nothing but RDDs. So RDDs definition itself says resilient distributed data sets, which means resiliency means if in any case uh, if a particular machine fails to do a data processing in the middle of a particular data processing, and if you want to recover that, we can quickly achieve that and start resuming the job or executing the job from the failed state instead of starting from the beginning. Now, distributed means once we read the data, we partition the data and distribute the data to multiple machines. So these two features provide us fault tolerance, data distribution, and parallelism, making them well suited for distributed computing environments. Hope this makes sense. And RDDs are immutable, meaning once an RDD is created, it cannot be changed. However, you can apply transformations to create new RDDs. So in order to explain this statement, I have a clear example here. And if you want to understand more about attributes of an RDD, you can read these points here. And you can pause the video and you can just take a look at them. Now, let's try to understand the meaning of once an RDD is created, it cannot be changed. However, you can apply transformations to create new RDDs. What does this mean? So the statement that was given refers to the immutability of RDDs in Apache Spark. Once you have defined an RDD, you cannot change its elements or its structure. However, you can create a new RDD by applying transformations to the existing ones. So let's try to take a very simple RDD. So this is a sample syntax to create an RDD using Scala. Now you'll use this function, which we not worry about right now, and you are using array data structure in Scala to define a list of 5 elements as an array and make that as an RDD. Now, suddenly you decided to square each and every number inside this array and you create a new RDD or change the existing RDD. You created one. After executing the statement, you decided to square this. Now you cannot change the original state of an RDD like this. So that's if you write the program, if you want to write or do the manipulation in Scala, you can do something like this. But this doesn't have, this is not applicable and when you're dealing with an RDD. That is not possible. Okay. So how do we make that happen? How do we want to change the numbers to have whatever the numbers that are present in this RDD to square themselves? So you can achieve that using transformations. So applying a transformation to create a new RDD. Instead, you can use a transformation like map to create a new RDD where the numbers are squared. So as you can see, there is a new RDD name, which is not the same as the old ones. Old RDD, new RDD. So, and we will apply the transformations of the old RDD. So the name of our old RDD is original RDD. Now you will apply your transformation on that old RDD, which is named original RDD. And as I said, Spark comes with some set of built-in functions, which we can make use of to transform our data. Now, map is one such transformation function available for us. And within the map function, as you can see, you want to square each and every element of the RDD, of that particular RDD. Now we are doing that. And similarly, you can chain multiple transformations together. Now, once you have squared each and every number, you might want to filter the values of that RDD based on the remainder value. Now, this is one more transformation that you can apply on that previous RDD. So this is the previous RDD state, and now we are making use of this RDD state to filter the data based on certain criteria. Now you might be thinking the syntax is too weird to write and too complex to understand at this point of time. So no one needs to worry about that, because we are not going to use RDDs much, because RDDs are still used in the underlying machines, but as higher level users or as end customers or developers, we do not write RDD code unless required in some specific scenarios. We prefer to write our entire data transformation logics either using data frames or data sets. So I do not want to confuse you right now, but We'll talk about the difference between these two in the coming sessions. Now, this slide provides a simple example about how to create an RDD. Now, this example is in Python, and as you can see here, I have taken a list with the name data, which contains some values, numbers as well as strings, and I want to create an RDD, and I'm using the parallelize method that is available in Spark, and then creating an RDD. So in order to make use of any Spark function, I need to use something called as a Spark context. So you might be wondering, what is this entire terminology and everything? So in order to use or make use of features of Spark along with a different programming language like Python, you need to have a particular variable that defines the connection between the end client and Spark and the Spark engine. Now, Spark context is the client-side object that represents the connection to a Spark cluster. Now, let's assume you have a big Spark cluster and you want to connect to that Spark cluster and execute your code. You have written your entire Spark code and you want to execute that in that particular cluster. Now, in order to do that, you need to have a token. It's more like if you want to go to a movie theater and watch a movie, you need to buy a ticket. So that ticket provides or authenticates or gives you a certain standard saying that, hey, this man or this woman has brought a ticket, so he is allowed to watch the movie in this particular theater. Similarly, I will get a token or kind of like a ticket which I'll make use of to execute my Spark application within a specific Spark cluster. You can compare the theater as the Spark cluster and the ticket as the Spark context, and the client is us. Okay, so Spark context is the client-side object that represents this connection to a Spark cluster. It's used to configure important parameters and create RDDs, accumulators, and broadcast variables on the cluster. We need not worry about all these terminologies right now, but what you need to understand is, in order to execute any Spark application, we need to have a Spark context created. Moving further, as I was continuously mentioning, once we read the data into a Spark from the file, then we immediately partition the data. And when I say always partition the data, that depends on the amount of executors and the amount of resources that you have. So just to give you a perspective, if you have 4 or 5 computers connected together, wherein each and every machine has Spark installed, and all of these are connected together. Now, if you read the data from a particular file, and then if you want to distribute the data of your huge file into multiple chunks and provide it to each and every machine, then Spark automatically does the partitioning for us based on our cluster configuration. When I say cluster, our cluster contains our 4 machines that we are talking about. So based on the amount of resources that are available, like a number of cores and the amount of space that is available, Spark automatically creates or chunks or partitions the data from a big file to small files, and sends that particular small data to each and every executor, and the rest of the things happens from there. We will close this particular session with this concept: transformations and actions. So a transformation is a function that produces new RDD from an existing RDD. If you remember in the previous slide, one of the previous slides, I've shown you we can chain multiple transformations together or multiple manipulations together. We are making use of the initial RDD that is created and using that to square the numbers. So we are using the previous RDD to do a transformation, and we are using this RDD to do one more transformation. Similarly, we can chain multiple transformations together. So transformation is a function that produces new RDD. Obviously, we are getting a new RDD when we apply a transformation from an existing RDD, which is what we have just seen. But when we want to work with actual data set, at that point action is performed, which means I'll show you a visual representation of what this particular statement means, but for time being, if you want to understand theoretically, when you execute this particular line of code in Spark, this happens very, very fastly. Let's say you have 100 gigabytes of data and you want to execute this statement. This happens very instantaneously because these are called transformations. So there is a concept in Spark called lazy evaluation, which I stated in a single line in the beginning of the session. So unless an action is performed on a particular set of data, the transformations will not be executed, which means there are a certain set of functions in Spark which are categorized as transformations and certain set of functions called actions. Now, transformations are executed fast. They are just specifying the type of logic that has to be executed on the data. Now, an action refers or provides a particular instance saying that, hey, whatever the transformations that were written or are compiled so far, just execute all those transformations on the data. So whenever we are calling an action function, we are going to say execute all the transformations that were written so far on the data that we want to process. So unless an action is not implied or not called, the transformations will not be executed on the data. So this concept is called as lazy evaluation. So when the action is triggered, after the result, a new RDD is not formed like transformation, because we are basically computing or doing all the computing till that point, right? Now, Spark transformation is a function that produces new RDD from existing RDDs. It takes RDD as input and produces one more RDD as output. Each time it creates new RDD when we apply any transformation. Thus, so input RDDs cannot be changed since RDDs are immutable in nature. Transformations are lazy in nature, of course. That is, they get executed only when we call an action. They are not executed immediately. And some of the basic types of transformations are map and filter. And some of the basic actions are count or collect, which means count means, let's say if you want to count the number of records in an Excel file or a CSV file, it's an action. So it is what are the functions that are defined are automatically categorized by default in Spark as transformations or actions. We just need to understand and learn them. We need not worry about learning and remembering each and every function available. We just need to understand the very basic and the most frequently used transformations and functions to get started with writing production level or production grade Spark applications. And rest of things we can always try to research and learn on the fly based on a given business scenario. So let's stop the session here. I hope you got a good understanding about the basic fundamentals of Spark. I'll try to upload as many sessions and as frequently as possible to explain more about Spark and try to give you a brief overview about Spark and Databricks in general. Thank you guys. Have a good rest of your day. Bye-bye.